Good morning, everybody. Today I'm presenting our credit card approval system for ABC Bank, built with responsible AI at its core. I'll be speaking to what matters to each of you directly. For our Chief Risk Officer, I'll be talking about whether this model creates an acceptable regulatory risk. For our Chief Compliance Officer, I'll be talking about whether it meets fair lending obligations. For our Chief Data Officer, whether the data infrastructure is sufficient. And for our CEO, whether this system is ready to represent ABC Bank's values to customers. So first of all, I'll be talking about our agenda. We have 8 sections today: business problem and dataset, then data preparation, metric selection, model performance and fit, and then our full responsible AI section covering fairness and explainability, and finally finishing with my recommendation. So, ABC Bank's current approval process is manual. So it's inconsistent and we cannot justify decisions to regulators. We need an automated system that balances accuracy, fairness, and interpretability simultaneously. Our dataset has 9,709 applications, and we're denied. So out of those, we have 19 features covering demographics, employment, and income. The critical immediate finding of this dataset was that 86.8% of the applications were denied, and only 13.2% were approved. This severe class imbalance has a direct consequence. A model that simply denies everyone achieves 86.8% accuracy without learning a single thing. Standard accuracy is completely meaningless here, which directly shapes our metric selection. So next slide, we'll be talking about data preparation. Before doing any modeling, we went through 4 data preparation steps. Step 1 was cleaning. Make sure there's no missing values. We dropped the ID column because it has no predictive value. We also dropped number of children because it had a 0.89 correlation with the number of family. That creates multi-collinearity issues, which means there's redundant information in the system. So we dropped that to make sure that doesn't happen. So step 2 is encoding. We had 5 categorical features: income type, education, family status, housing, occupation. For that, we used one-hot encoding with PD get dummies, giving each category its own dedicated column. We specifically chose one-hot over binary encoding because 3 models can directly learn that income type student equals 32% approval rate when student has its own column. Binary encoding fragments this into bit patterns across multiple columns, making it impossible for trees to extract that clean signal. This expanded our feature space from 19 to 52 features. And step 3 was scaling. We applied standard scaler to the 5 continuous features only: total income, age, years employed, number of family members, and account length. This removes unit differences and puts all continuous features on the same scale. The one-hot encoded columns are already 0 and 1 integers, so they don't need any scaling. And finally, step 4, handling class imbalances. We used SMOTE-NC, synthetic minority oversampling technique, for nominal and continuous features. Standard SMOTE would create fractional values like 0.4 for our binary column that must be 0 or 1. These are invalid and will corrupt our samples. So SMOTE-NC handles mixed data types correctly. Critically, we applied SMOTE inside cross-validation pipelines only on training folds, never on the validation folds, to prevent data leakage. We also preserved gender separately before any processing as our sensitive attribute for fairness in this analysis. So next is metric selection. With 86.8% class imbalance, we needed a metric that actually means something. As shown on the top of this slide, accuracy is completely rejected. A model denying everybody hits 86% accuracy without learning anything. We will not use it. We selected 2 metrics. First, AUC ROC as our primary. The area under the curve, receiver operating characteristics curve. This measures the model's ability to discriminate between approved and denied applicants across all possible decision thresholds. Not just one, this makes it completely robust to class imbalance. 0.5 means random guessing. 1 means perfect. Our dataset ceiling after exhaustive testing was 0.582. Second, F1 score on approved minority as our secondary. You might ask, why not report precision and recall separately? The answer is F1 is their harmonic mean. It already encodes both in a single number and penalizes models that sacrifice one over the other. Reporting all 3 would be redundant. Precision as for our approved predictions, and how many were actually correct. Recall asks for truly creditworthy applicants and how many to be fined. High recall means fewer creditworthy applicants wrongly denied, which is critical business and ethical concern, especially in credit approval. So now we're going to be talking about model selection. We trained and compared 4 different classification models using a 5-fold stratified K-fold cross-validation method, using SMOTE-NC inside the pipeline to prevent leakage. Logistic regression as our interpreted baseline, we can see we achieved an AOC of 0.528. It's good for understanding features directly, but limited by a linear decision boundary. Random forest gave us an AOC of 0.545, slightly higher, because of, ensemble because it's an ensemble of decision trees. It's robust to noise, provides built-in feature importance. This is also there. XGBoost, actually even slightly higher, with gradient boosted trees strongly on tabular data. We chose random forest over XGBoost only because it actually was more compatible with our explainability tools such as SHAP, SHAP, Lime, and PDP, which are central to our responsible AI implementation. And finally, LightGBM with an AUC of 0.538. Fast gradient boosting, comparable performance separately. As our exhaustive benchmark, we ran an AutoHTML. AutoHTML is basically an AutoML model that automatically runs through our dataset and finds the best performing models. So the best performing models, the ceiling AOC we basically got after running the H2O AutoML for 10 minutes was 0.582. So that was a stocked ensemble method. So basically this is telling us that no matter how much we try, it's basically like that's our higher ceiling for our performance for this specific dataset. So next is our diagnostic journey. All four models and every configuration produced an AUC between 0.52 and 0.58. We systematically diagnosed Y across 5 attempts. Attempt 1, standard SMOTE with binary encoding gave us an AUC of 0.52. We discovered SMOTE was interpreting between binary encoded columns, creating fixed fractional impossible values. We fixed this by switching to SMOTE NC. Attempt N2, SMOTE NC with binary encoding gave us AUC of 0.54. Performance barely improved, ruling out oversampling as the root cause. Attempt 3, we switched to one hot encoding for binary encoding. So this gave tree models interpretable category splits, found and fixed a Boolean D-type issue, and attempt 4 was basically a critical test. We ran a vanilla random forest without any changes, and with just label encoding and zero pre-processing, and the AUC was still 0.55, basically the same result. So this confirmed that our pipeline is not the problem and the ceiling is in the data itself. And finally, attempt 5 was the AutoML. So we ran the H2O AutoML for 10 minutes. Best results gave us 0.582. This is the definitive ceiling confirmed. So no credit, the dataset lacks financial features needed for reliable credit risk prediction. No credit history, no debt to income ratio, no repayment history. This itself is a major finding, at least in terms of responsible AI findings go. So next we're going to be talking about model performance and fit. So before tuning, our random forest achieved an AUC of 0.542, but an F1 of just 0.077 on the approval class. This means only 6% of the recall on creditworthy applicants. The model was denying 94% of genuinely creditworthy people. That is not just poor performance, it's an ethical failure. We ran grid search CV, or it's a grid search cross-validation method, to tune hyperparameters. The optimal configuration was max depth of 5. Minimum sample leave of 5 and 200 as estimators. Constraining tree depth to 5 is key. It prevents the model from growing deep enough to memorize noise, directly addressing overfitting. After tuning, AUC improved modestly to 0.546, but F1 jumped from 0.077 to 0.2, and recall on approved applicants went from 6% to 59%. This is the accuracy fairness trade-off in action that we always see. The tuned model is less conventionally accurate, but dramatically more ethical. Our learning curve analysis shows that exactly what's happening. Training AUC reaches 0.99, severe overfitting. The model memorizes the training data perfectly. Validation AUC sits at 0.54 with a gap of 0.45. Critically, this is not underfitting. The model has a sufficient capacity, and the validation curve is completely flat as we add more training data. This rules out a data quality problem entirely. The features themselves lack a genuine predictive signal. This is a data quality problem that no modeling technique can overcome. So next is our responsible AI and fairness analysis. So fairness in credit approval is both an ethical requirement and a legal one under fair lending regulations. We use FairLearn's metric frame to measure 2 fairness criteria across gender groups. Selection rate, also called demographic parity, requires equal approval rates across groups. True positive rates, equal opportunity, requires that of all genuinely creditworthy applicants. Equal proportions across groups are correctly approved. Before mitigation, the results were alarming. Male applicants were approved at 66.6% versus 46.8% for the females, a 20 percentage point gap, a selection rate disparity of 0.89. More critically, the model correctly approved 77.5% of qualified males applicants, but only 49.5% of qualified females, a TPR disparity of 0.28. Qualified women were being denied at nearly twice the rate of qualified men. In such regulated industries, This would constitute a serious fair lending violation. We applied Fairlean's threshold optimizer with an equalized odd constraint. This is a post-processing technique. It adjusts decision thresholds separately for each gender group after predictions are made, optimizing for equal error rates across groups. The results after mitigation are transformative. Selection rates disparity dropped from 0.98 to 0.004, near perfect demographic parity. TPR disparity reduced from 0.82 to 0.0058, a 79% reduction. And overall accuracy improved after mitigation, showing that in case of fairness and performance, in this case, fairness and performance are not in conflict. In fact, they go hand to hand. So next, we're going to talk about global explainability. Global explainability itself tells us how the model behaves on average across all applicants. We applied 3 complementary methods, each explaining different dimensions. Random forest feature importance uses Gini impurity. It measures how each feature improves the model's decision tree split across all 200 trees. Account length dominated at 0.293, nearly 5 times the next feature. Gender ranked 7th, confirming the model uses it as a predictive signal. SHAP, Shapley additive explanations are grounded in cooperative game theory. The idea is that each feature is a player in a game, and its SHAP value is its fair contribution to the final prediction, calculated by considering every possible combination of features. SHAP confirmed account length as dominant with mean absolute impact of 0.04. But SHAP adds something feature importance cannot: direction. High account length pushes strongly towards approval. Being female has a negative SHAP value, confirming gender bias at an individual level. Partial dependence plot freezes all other range, vary one feature across its range, and plot the average predicted probability. Account length shows a clear monotonic positive relationship. Longer tenure means higher approval probability. Age shows a counterintuitive negative relationship. Younger applicants are favored, which contradicts traditional credit risk thinking. Income is near flat. Surprisingly weak for a credit model. All 3 methods plus H2O XGBoost variable importance independently all ranked account length number 1. This cross-method, cross-model convergence makes this finding highly credible. This model is deciding based on customer loyalty, not financial creditworthiness. Next, we'll talk about local explainability. While global explainability shows overall behavior, local explainability explains individual decisions, which is what applicants and regulators actually need. We applied all 3 local techniques to one case study: a denied female applicant, young, employed as a secretary, low income, average account tenure, with an approval probability of 0.47, just below the 0.5 threshold. Lime is a local interpretable model agnostic explanations. So it creates thousands of synthetic variations of these applicants, runs them through the model, and fits a simple linear model to understand the local decision boundary. Lime found 2 dominant denial drivers: secretary occupation pushing -0.04 towards denial, and average or below account tenure at -0.03. SHAP waterfall plot starts from the baseline expected value of 0.487, shows each feature's exact contribution. Secretary occupation contributed -0.038. The single largest factor, account length, actually contributed plus 0.017 towards approval. Gender contributed -0.017 towards denial. Small, but definitely present, confirming individual level bias. Lime and SHAP agree on key drivers, which both validates explanations. The counterfactual analysis in the most striking finding, changing occupation from secretary to anything else alone, raised approval probability from 0.47 to 0.52. And approval, increasing income by 2 standard deviation alone changed nothing. Increasing tenure by 2 standard deviation alone changed nothing. A job title alone flips the decision. A secretarial role are disproportionately held by women. A model where occupation title matters more than the income is encoded occupational stereotypes. A form of proxy discrimination that must be investigated before any deployment. And finally, I'd like to give my findings and recommendations. 4 key findings and 5 concrete recommendations. We found data signal no model exceeded AUC of 0.582. This current data lacks credit history, debt ratios, repayment history, and repayment history needed for reliable scoring. Gender bias. Women approved at 47% versus men approved at 67% before mitigation. A 20-point gap, violating a fair lending standout. Occupation proxy, a secretary job title alone flips a credit decision. Tenure versus merit. Account length dominates every model across every technique. Loyalty is being confused with credit worthiness. From a value proposition perspective, if the bank invests in richer data and well-governed model, the upside is real. Faster approval reduced operational costs, consistent decision reduce legal exposure, and transparent explanations improve customer trust and retention. 5 recommendations. First, do not deploy this model. AUC of 0.58 means marginally better than random, but regulatory and reputational risk is unacceptable. Second, collect better data. Credit history, debt-to-income ratio, repayment history, and external credit scores are standard in a credit risk and would dramatically improve signal. Third, implement continuous fairness monitoring using FairLearn metric frame in production. Fourth, audit occupation based on decision rules. Secretary occupation alone flips decision. This warrants a proxy discrimination investigation. Fifth, mandate explainability for every denial. Applicants have a right under financial regulations to understand why they were denied and what they can do about it. Responsible AI is not a constraint on performance. It's a prerequisite for trustworthy, regulatory, compliant, and sustainable development. Thank you very much. Full technical analysis, all code, and complete reproducible results are there in the Jupyter Notebook, and I'm happy to take any questions. And feel free to leave a comment if you have any suggestions or any questions. Thank you very much.